But this is our practice, wearing our sector appropriate gear. We don't make everybody dress as lumberjacks all of the time, but we like to tell the story firstly about what we're interested in, but also the story that we're not a huge practice. There's about 30 people in our practice, 25 when I wrote this, more like 30 now. We've been a practice for around 25 years. And we think that we are world leaders in designing in timber. We think that we punch above our weight in terms of the size of our practice and our reach and what we do around the world. And first and foremost, we like to make sure people remember that we're not just wood people, we're architects. It's really important to us that the architecture comes first, that really, really high quality buildings are the things that we aspire to do. But the way that we do that is to do that in the lowest carbon way that we possibly can. And in order to do that, we generate new knowledge. So about 20% of our practice's work is in primary research directed at sharing that knowledge and sending it around the world to help others to do the things that we as a small practice in East London can't do. We do that internationally. We currently have live projects on each coast of the US, one in Italy, one in the Netherlands, even one in Portugal at the moment in a very early stage. But we also do the sharing of our knowledge and the research base and all those other things internationally as well from our base in East London. We've completed about 28 mass timber buildings now. There are many, many more that we have designed that haven't been constructed for one reason or another. And we do those at all manner of different scales, whether it's a very small pavilion like the one you can see on the left of your screen, all the way up to kind of almost city scale and designing urban plans that aim to reduce our reliance on carbon and aim to deliver projects in mass timber as well. So why do we do it? Why is wood important to our practice? Well, this graph here shows where all of the environmental greenhouse gases come from every year. This is a slightly out-of-date graph, I think maybe 2018 from the World Resources Institute. But if you look at the figures for iron, steel, and cement and add those together, you'll notice that those figures are pretty much the same as the energy in use from all residential buildings in the world, about 11% of emissions. Now, we have lots and lots of policy, lots of effort has been made over the last 20 years or so to reduce the amount of energy that we use operating our buildings, turning on our cooker, driving our cars, doing all those sorts of things. But almost no attention has been paid to what we use to manufacture those things. And buildings in particular contribute massively to that, iron and steel and cement. So we have two figures that are about the same. We're working really hard on one of them, but not on the other. And that's really important to us because when you think about the emissions from a building, on this graph, what you can see is that on day one, if we call it 2022, all of the emissions that have been caused by that building come from its construction, 100% in materials on day one. Now, after, say, 50 years, that balance shifts. Of course, we sleep in our buildings, we turn the lights on, we turn the TV on, we do all those sorts of things. Gradually, the proportion allocated to operation creeps up. And after 50 years, yes, most of the energy comes from operations. But I think that none of us are talking about having 50 years to change the situation that we're in. We haven't made commitments the last 50 years in terms of reducing our carbon output. We've made commitments on much, much shorter timescales. And if we take arbitrarily an 18-year lifespan, probably far too long in the first place anyway, in terms of reducing our use, at that point, we're still talking about 70% of the emissions from a new building built today being from the materials we use to build it. And currently, we're doing very, very little to change that. Now, for us, we think it's really important that building professionals, architects, building procurers, people who buy buildings, building contractors, have a responsibility to own this, because the impact we can make on changing that metric, on changing that emission of carbon, is vastly bigger than an individual. An individual making a choice to no longer eat meat will make one kind of impact, but we can multiply that impact by 10 times, 100 times, even by making very, very small changes in the way that we practice. Not even necessarily on every single building that we design, but we have to try and we have to multiply our impact that way. And so for us, the crux of this is the opportunity that we have from timber. So by using timber, we can take out iron, steel, and cement that you saw as being massive contributors to greenhouse gases and global warming, and we can replace them with a material that is much lower in embodied carbon. It takes much less carbon to produce. But more importantly than that, this is a material that takes carbon out of the atmosphere during its lifespan, and that we have the opportunity then to put it into a building where that carbon can be locked away for 50, 60, even 100 years. Even better if you look at the context of the Canadian wildfires that we're seeing at the moment, where if we leave them in the trees, they're susceptible to going back into the atmosphere. But if we lock all of that carbon into our cities and create a massive carbon sink in those cities, we can store that carbon safely, manage it, grow more trees, take more carbon out. So to us, what's really interesting is the idea that this is the only technology that isn't only talking about slowing down our impact on the planet, but in fact hoping to try and do things that might slowly reverse it. I said that there's very little policy about this. I mean, when I started giving this talk, there was almost none. But I think the other reason why wood is because actually quite a lot of the world has realized that this is the thing that we need to do. And here is a map of all the countries in the world that have on some level legislated to try and encourage people, A, to reduce the amount of energy they use making things, so that embodied energy, but B, in a lot of cases, specifically mandated policies that require people to start to use timber to create these city scale carbon sinks. It's happening at national level, it's happening at regional level, it's happening at local level. So there is a real need for the industry to start to understand properly what does it mean to try to build buildings in wood. Some of you will know lots and lots about mass timber already. You may well have just heard quite a lot. Sadly, my Portuguese isn't up to understanding what's been said already. But a quick guide is, many of you will have heard this acronym CLT. So cross-laminated timber. That is one kind of mass timber. I think what's important to say is that it's solid wood all the way through. That product consists of 3 to 7 layers of softwood normally bonded together, but the important part is that each layer is turned through 90 degrees in order to give that spanning properties that work a little bit like a concrete slab with reinforcement. It spans in more than one axis. So it's enhanced in its performance from a single piece of wood that in its natural state only spans in one axis. What's great about this material is that it's accurate. It's made in factories, it's made in safe environments, it's predictable, but also it does what it says it will do. So we know that the performance of a CLT panel is very, very likely to be incredibly close to what we predict it to be, unlike materials like concrete, for example, that are poured on site in the wind, in the rain, in varying conditions, and we never quite know what performance we're going to achieve. Again, what we have is that opportunity to lock away carbon, but we also have that opportunity to create a cycle, to kind of be really circular in the way that we use our materials and put that back into the atmosphere and back into the environment that we use to create it. What's really important is CLT is the kind of the famous, the buzzword of the moment, the thing that everybody's excited in talking about. But actually for us, it's really not just about CLT. It's about really carefully understanding the whole ecosystem of these timber products that we can use to start to capture that carbon from the atmosphere and put it into our cities. And actually, there's real nuance in choosing these different materials, which we'll show you through some of the case studies that I'll put up on the screen in a moment. But to us, what's become really important is the idea of thinking of mass timber not as an individual product that you substitute in for concrete and swap the gray stuff for the yellow stuff and everything will be fine. Actually, there's a lot more to understanding how to build in timber. And that has been a real focus of our research over the last few years. And key to that is understanding the idea of timber and mass timber as a system, as a combination of elements that need to work in harmony together. We simply cannot design concrete and steel buildings and substitute out one material for another and expect to get really good outcomes in terms of carbon and indeed cost. So for us, the first step was to begin to try and construct some of these buildings, learn by doing. And when we built Murray Grove, that was not our very first timber building, but certainly the largest. At the time, it was the world's largest. It was 9 stories tall. It was built incredibly quickly, incredibly quietly, in a clean and safe way. But at the time, no other building in the world in mass timber had been built at above 4 or maybe 5 stories. So to us, it's an incredible learning experience. It showed us what the barriers might be to constructing a mass timber building at this height, showed us how to try and overcome those. It showed us how to have conversations with clients to explain to them why they might choose to work in this way. But the most interesting learnings for us were around the idea of walking onto this site, smelling the wood, seeing how low technology actually it could be to assemble this with an incredibly small team of people, and being on what seemed a much cleaner, safer, nicer building site than all the ones we'd been on before. And even the neighbors found the same, no cement trucks driving up and down the road, no jackhammers, electricians that could staple installations onto the ceiling rather than loading jackhammers onto their shoulders and hurting themselves by drilling holes to fix small screws into concrete soffits. It also taught us what the design parameters for mass timber buildings were. Here, of course, as you can see from this image, we're building in panels, so panelized CLT as a system entirely on its own. And so we had to learn what the logic of designing a panelized building was compared to the logic we'd always been brought up with, which was to design column and slab arrangement buildings. Interestingly, because of the learning process we were on, we reckon there's about 25% more wood per square meter in this building than our modern mass timber buildings that we're building 15 years later. And that I guess, shows the distance of the journey that we've had to go on over the years. But maybe an interesting example of how we jumped forward in that process is to show you Dalston Works. So this is a building completed 10 years after Murray Grove. The building extends from the left of the scaffolding here to the right-hand side, so a much more significant building. Here we were doing not just the tallest, but the largest building in the world, 121 homes, 35,000 square feet, or 3,500 square meters in metric, of office space as well, and going up to 10 stories. So not actually much taller than Murray Grove, but I think for us, this was about proving the idea that we could do much more significant buildings. We could do them for developers that weren't in themselves especially interested in sustainability, but we could prove that this could be a normal way of building buildings. Here you can get a sense of about the difference in scale that we're talking about. So if I flick back, Murray Grove would have been this one core of the building. Here we have a building of 7 cores just 10 years later, built again, not for clients that are looking for a unique one-off building to prove how sustainable they are, but trying to make the difference with clients who maybe don't have this as their primary agenda, because that's where we can make the biggest difference. But still, for this much bigger building, you can see the same simple connections, the same CLT panels, the same site managers wondering when the crane is going to land and drop the next panel into place. But here we started to learn how to have conversations with developers who aren't interested in sustainability and carbon, don't understand why they should do better when, of course, there were no rules around embodied carbon, as I said at the beginning. Now here we had train lines underneath. You can see the dotted lines that sort of constrain the site from building heavy buildings. We were able to talk to the contractor more about, we can build your building 20% faster. So if you've borrowed money, you can make more money. We can build 25% more homes because we can build the whole building on a 90 centimeter thick slab with no piles, which we couldn't do with a heavier concrete building. So we were learning to talk the language of our clients rather than the language of sustainability to ensure that these messages could get across. And of course, for these sorts of clients, what's really important to them is that it looks just the same as all their other buildings. And so that's what we proved. A building clad in brick, maybe not the brightest idea to put heavy materials on lightweight buildings, but we were able to prove to them, hey, you can have more money, quicker building, less borrowing, and ultimately the same product that you sell every day. So why wouldn't you do this? Why wouldn't you save carbon and build in this way? Now, part of that journey was learning to build in other materials and learning to build in other sectors. 6 Oarsman Road was our first really significant office building. This allowed us to investigate lots of other themes that we're talking about, the idea of passive shading of the building, bigger ideas of how buildings can be sustainable, using lightweight cladding materials to show that we can have a back-to-back process with factory-made cladding to go onto factory-made structure, and also looking at hybridizing the building in certain situations, using a combination of steel and timber to do as much as we can in every individual building. If we can't build the whole structure out of wood, maybe we can use some wood, reduce the embodied carbon, but compromise in certain places. And this building also was the start of our journey in thinking about demountability. So every single connection here is a bolted or a screwed connection. There are no welded connections. We know that we can take this building apart if a component fails, if we need to change its performance, and we can keep that carbon in the CLT for much longer if we know that later we can take it apart and use it in another place, or repair it, replace it, extend the life of the building. Still, we're exploring here the idea of sharing that beautiful material, although that's never our primary aim. Primary aim is carbon. But here we started to be able to explore what is an architecture of mass timber in these spaces. And even during the course of construction, we were able to prove our ideas about demountability and reconfigurability by installing this staircase after we'd completed the building to meet some new fire regulations. So actually, all of the treads of this staircase are the CLT cut from the floor above the stair when we had to make that hole to deliver it. So we're starting to prove some of those ideas that we're thinking about. Now, as we started to prove, as we started to deliver and build real buildings, it was important to us to work out how we can collaborate, share, put that knowledge wider into the world. The first document that did this was the CLT 100 UK book. We actually produced this as a study for the Binational Softwood Lumber Association, which is a collaboration between US and Canadian State Departments. And this was a study of 100 projects that already existed in mass timber in the UK, aiming to show to people that this is not brand new. There is data, there is learning from all these projects. And this was used by the Binational Softwood Lumber Association to start to lobby for and talk about the idea of building code change in the US. And I'm happy to say that in a few states, they now have been able to secure that. But this was the first attempt at gathering together what we know and sharing that as a how-to guide and as an evidence base. Moving on from that, we've been doing work in the UK housing sector. You may know that there have been some challenges in delivering housing following on from the Grenfell fire in the UK. What we wanted to do was prove to people that none of those changes meant that you cannot build residential buildings in timber. So we gathered some funding, we gathered some partners, a really exciting team of people, to put together a document that proves that you can build this. It consists of a series of individual principles, a performance specification, details, and here you can see us starting to investigate that idea that even though each building could individually be different geometries, different shapes, we start to talk about delivering mass timber as a system. If you apply these principles of this specification, if you apply them in the way that we have developed these color-coded, performance-based details, and if you build them in the sequence that makes sense and is approved by other parties, you can deliver in mass timber without taking on this personal risk and liability of learning each time as a bespoke product how to deliver within the building codes that you're working with. What we're also able to do in the new model building process was to quantify what the benefits of that are. So here you can see that if we compare a typical building we designed using these details with a concrete building of the same scale and the same arrangement, we're looking at 74% potential reduction in the embodied carbon of that building. So if you go back to my earlier graph of saying, you know, on day one, 100% of our carbon emissions are from embodied carbon, well, now we can reduce that by 74% for a timber residential building between sort of 3 and 6 stories in the UK using this systematized approach to building. And of course, from all our learnings of building buildings before, we know that clients who don't have to do this want to know what's in it for them. So we're able to quantify that in terms of costs. It's a 5% capital uplift. We're looking at thinking that there are going to be carbon taxes of maybe 120 euros per ton in the next few years. The moment you compare that 74% reduction in carbon with that 5% difference in capital cost, you can see that as soon as people start to look ahead to all those policies that I showed you emerging across the world earlier, when those policies start to turn into money, that 5% is going to be a saving, not an extra cost. So we're able, through research and through publication and through collaboration, to start to prove the logic of the things that we knew intuitively and start to demonstrate the things that we've studied through doing. Finally, in our research bit, we're also able to share that across the EU. So we're just coming toward the end of a 4-year funded research program with the European Commission. That's part of the Horizon 2020 fund. And the idea of this is to take those ideas of systematization, expand them across a massive set of different available mass timber systems, all that diagram that I showed you before, LVLs, glulams, CLT, and apply that same idea of layers of information and categorization of components into a system and make it in such a way that we can create a kind of how-to guide, which will be expressed as a website, which will be free to use, which it explains to anybody in any individual territory in the EU how you will meet your local building codes under the headings of vibration, fire, acoustics, whatever it may be, by applying other layers in a systematized way to achieve your local building codes, because we have that evidence. We're currently now building a demonstrator building, a prototype building with the Danish Technical Institute in Copenhagen, and that will come along with new test data that proves the way that we're doing things. And all the time it overlays other things we're interested and excited about. So even in this process, we've identified new demountable timber-to-timber connections that have been developed by Rotherblast based on the outcomes from this research. And of course, that will be published as a very big book. So I'd encourage you, when the time comes, to go and look at the website and Configurator as an easier way in. But really, this is about us multiplying our reach as a small practice with a particular excitement and a particular passion, to share that with the rest of the world, to make the kind of size of impact that we need to do. Maybe this should be the first document, but it's our most recent, so it comes at the end. This is also wheeling right back to the beginning of the conversation, a document you can download right now, volume 1, which starts to tell you from very first principles, what do we mean when we talk about mass timber? So this is a great document for sharing with teams in your office who might never have come across this before, talking about those individual components from that graph I showed you earlier, of the different ways we can make components out of timber, showing you what that means in terms of systematization, and giving you rules of thumb. How big can it be? How far does it span? Why would I choose glulam versus panels versus timber frame? Now, having done that, we've been on this big loop of learning by doing. We've tried to codify that, share that, enhance that with testing and primary research and data that we can learn from partners from across Europe and indeed across the world. The next thing is to start to go back and apply that back into our work. So on a very small scale, we were able to look at those ideas of volumetric and modular design, ideas of demountability, with this pavilion that we provided for the American Hardwood Export Council. We were also able to investigate new species here. So this is tulip wood, which is in oversupply in the US, and AHEC, the American Hardwood Export Council, they commission a pavilion in this every couple of years to promote that material for use over here in Europe, so it stops being used for fuel and going back into the atmosphere. And we said, well, hold on, why are you making a pavilion every year and then throwing it in the chipper? That's the opposite of what you're trying to achieve here. We said, why can't we make this at home in the UK, the first ever CLT panels pressed here, albeit without with American lumber. And then let's make it into something that we can take apart again and reconfigure and show to other people. So what we did was exactly that. The first one you saw was in the Victoria and Albert Museum courtyard in London. We took it apart, reconfigured it for another location in London, for another design festival. And then we took it on tour. So we took it to the Milan Furniture Fair. We took it onwards to Madrid for a design festival there. We were on our way to Venice when COVID hit. So sadly, that one didn't happen. But here it is in Milan. Here it is in Madrid, and now here it is, part of it back in London and the rest stored in a warehouse. So again, we're testing these ideas that we've had in research and in buildings, prototyping them on a small scale, then implementing them in bigger scales. So we were able to start to think about how these demountable, modular and reconfigurable designs might work for housing. So here, this was a project where we used our newfound skills in codifying and sharing to design a system that underpinned a whole new factory built by a housing provider in the UK. They wanted us to work through and understand by doing what their system ought to be, and then codify it, turn it into documents and share it so that other architects could work with their factory to design their next building. And of course, none of that's any good unless you actually do it. So here are the first modules being constructed in the factory. Here they are leaving for site, and here they are being erected into the building that you saw at the beginning of this little section of slides. We're expanding that into other sectors. We're taking that same systemization approach and idea into industrial buildings. This is a system you can buy today from Store at Enso's website. They very kindly invited us to help them codify the different decisions you might make when procuring industrial buildings. It's another sector where we can and should be reducing our carbon impact and using timber. The whole thing is there like a configurator. So if you were to buy a car tomorrow and go online and you wanted to know how much it cost you for that leather seat or for that air conditioning or for a CD player, if you've still got a pile of CDs lying around somewhere, I don't know. This is exactly the same process. So you go online, you choose the parameters for your project, the size, you can download details, you can download 3D models. That will give you a volume of timber, which can quickly get you a cost from Stora, and you're able to go and buy it today and go and build it. That principle is based on this idea of pixelization, I guess. So what is the right resolution of standardization? We think that standardization shouldn't be whole buildings. You shouldn't go and buy a whole building off the shelf. You should have choices, but we need to know at what level we standardize. So if we take examples from the car industry, it's not about using robots. It's not about using pulse line manufacture. It's about understanding what should be standard and what should not, because car factories don't make things. They buy things and they assemble them. And a really great example here is the Mitsubishi platform, which is wheels, chassis, engine. That Mitsubishi platform creates vehicles that are as different as the Lancer, a kind of sports vehicle, versus the Jeep Patriot, a completely different vehicle. They have the same component at the middle. So it's about working out what scale should we be componentizing, what scale should we be standardizing, and actually from a standardized system, you can get all of these different variations. And we've learned that through really understanding the different materials, processes, products that are available in the timber industry, understanding the supply chain, and understanding how they all work together as a systematized approach. And of course, they don't have to be ugly. So a few images here to explain exactly what the environment might be like in some of these buildings and what they might be used for. So at a different scale, we applied this to a project for Lend-Lease in the north of Milan at the old Expo site. The principle here was that Lend-Lease said, well, we like this idea of systems, but we're going to have to build hospitals, schools, offices, homes. How can we develop a €2.5 billion master plan over 15 years using a systematized approach? And we said, well, what we need to do, again, is work out what's the right size of thing to standardize. And what we established for them was that a working prototype would be this 9 by 9 meter grid, which we knew could give the flexibility to deliver all the things they wanted. Each of these components could be called off from the factory exactly the same every time and have the flexibility to deliver the things they want. And it could be backed up, just like a car factory buys steering wheels from different places, buys leather seats from different places to assemble them into one. It could be backed up by a kind of hinterland of other products that can be standardized to meet it. And if we multiply that by a number of floors and layer that up with different products, you can see how we can create buildings and how that can be multiplied into whole campuses of different proposals, each entirely suited to its own function, but based on that standard 9x9 grid that is the beginning of it all. And of course, again, to our mind, we think we're able to create beautiful buildings, great spaces that are environmentally responsive and do all the things that they need to do. But all of it from this first prototype, which is available to go and see right now at the Perceptions of Timber exhibition in Milan. And this is a very different understanding of some of those materials. It's a very different set of components, but it's that same idea of understanding materials, turning them into systems and components, and multiplying those to create the delivery of low carbon, efficient products for living in. So this is the squishy bit of the presentation. I've gone pretty quickly. We're at 22. I'll try and get through this section quite quickly because it'd be great to have questions from you. But maybe I'll flick very quickly through the last couple if we're running out of time slightly. This is about the buildings that we are recently completing, that we're working on into the future, that maybe test even more exciting to us, at least, and novel ideas. The black and white building is one that we completed earlier this year in London. It's been very popular. We've shown over 600 visits around this building during the course of its construction and after its completion. And it's interesting to us because it's a building where the client was really engaged in designing the building with us and also really wanted to tell the story of sustainability. So unlike a lot of the buildings we've built, there is lots and lots of exposed timber. It's really easy to tell the story. And we can start to build real evidence for these ideas that we've been having and tell them through data, tell them through experience. So for example, we have a building here where the basement, a single story of accommodation, took 38 weeks to build, but 6 floors of accommodation above that took only 14 weeks. That was erected with between 4 and 6 people on site at any one time, a tiny number of people. The neighbors were worried about noise. Their noise monitor went off once during the 18 months of construction. The reason it went off was because they had their own party. This is quiet, quick, neighborly construction. This is also a building that really leverages 15 years of knowledge in different structural systems. We were able to identify the use of LVL, which is a very under-recognized, a very rarely used material in the mass timber space, which gave us an amazing economy of material and allowed us to get the big open spans that we needed, but with the absolute minimum of material and therefore the minimum of cost. But also we started to think about the architecture in the way of what is this architecture of sufficiency? What's the minimum we can use? So we started to use the computer and parametric tools that we started to learn through standardization and factory manufacture and apply them to designing a responsive facade. So we applied some path data and the shadowing of nearby buildings to the facade to create a heat map, which allowed us to choose the absolute minimum amount of timber to clad the building in. You can see it's more opaque at the top where there's more sun, less opaque at the bottom. So always layering these ideas across, but ultimately resulting in the same process. Really simple, quick manufacture with small teams, simple connections with bolts that can be taken apart again in the future simply by drilling out the little plugs that form the fire protection over the top of them. And here you can see, when I talk about using 25% less timber on our buildings now, you can see the absolutely tiny amount of wood that is going into making these big open spaces through our really detailed knowledge of how to choose and combine these materials now. This building was about just over 1,700 trees, but the amount of wood in that building, if you think of those trees growing over the course of a whole forest rather than an individual tree growing over 30 years, there's about 52 minutes of wood in that building. So we really can be doing more and more of this without damaging the capacity of our forests. But really important is to start to prove the numbers behind what we say we're doing. So the pie chart on the right is the equivalent building had we designed it in concrete. That would be about 662 kilograms of CO2 equivalent per meter squared across the building on the day that we open. So we've saved about 1/3 of that carbon by building in wood. We can definitely do better. 37% of that comes from that concrete basement. So there's definitely things we can improve. But if we then also include the carbon that's stored inside that building, we get a much, much smaller number, 256 kilograms of CO2e per meter squared. So we really think we can make a massive difference compared to building in concrete, even with concrete basements and things that we need for other reasons. Here again, you can see that breakdown, the concrete and the mechanical installation being the biggest parts of that. So here's some images to flick through really quickly. This is what it looked like during construction. Here's an image to prove we did what we said we would do. So the CGI from design development is on the right and the finished building on the left. And here is the facade with those changing stepping louvers that respond to the daylight conditions in different places. And again, the eagle-eyed amongst you will notice that this is tulip wood. This is what we were using on that pavilion, trying to prove that it can be used for buildings, that carbon can be locked away. So this is the world's largest heat-treated tulip wood facade, proving that we can deliver that material into building projects and keep the carbon within it for the longest possible amount of time. Another building we're really proud of in that space using similar technologies is Vitsu. This is a manufacturing facility for furniture, for shelves. Their question to us was, we produce a really high quality, quite expensive shelving system. We tell people to buy a little bit now and change it as their life goes on. It's a system. Why don't people understand? Why can't we have buildings that work as systems where you can buy a little bit now, you spend a little more because you know you can change it and adapt it as you grow older? Well, actually, we said, yes, that's exactly what we're interested in too. So we took these ideas of systemization. We developed their building on a long linear site as a series of, I think, 17 bays on day one. And we told them how they can go and extend the building in the future by calling off extending in linear fashion. Here you can see the building on the site and the space at each end to maybe extend that building in the future. But we also thought about extending in the short term. So here, hopefully you can see my pointer in the distance. There's a little beam between the columns, which supports a floor above and a staircase. Here you can see there is no beam. But here on the floor of the warehouse are beams ready to slot in if they want to extend their factory inside in the future. And of course, being a factory, they have things like forklift trucks. So they can ably change the environment in their factory from day to day pretty much, but still have a really beautiful, welcoming, humane environment for their employees to work in. Okay, flicking really quickly through the last bits. This is a little illustration of how we can change that and think about that on city scale. This is reclaiming a part of the lake in the center of Bergen using reclaimed rock from the latest tunnel that they've bored through one of the mountains that surrounds the city. The idea being to drop that into the lake, but also use that to grow oysters, which can help filter the water and clean the lake. Oysters already being native to the lake in Bergen. But this is where we started to think about how do we employ those ideas and think about town planning that is sustainable, that gives best access to daylight, that allows breezes to cool our buildings rather than sun to simply heat them up. And thinking about how we organize at a city scale to be sustainable, always building with wood, always thinking about the same materials, but overlaying other bigger scale ideas. Similarly, we started to look at how we can retrofit structures. So this is a tower in London. We took this to detailed design. Unfortunately, for lots of reasons, COVID being one of them, it didn't happen. We were able to tell the story of how we can enhance existing buildings, extend their life, renew them by using lighter, high-tech, strong timber materials, talking about how if we were to fill in the corners of this cross-shaped tower, we could do that in 36 months. It would take us 5 years to knock this building down and put it up again. But think of the carbon, think of the time, think of the cost. So again, building on all those conversations we've had to start to think about things in different ways, start to think about how our systematized approach and offsite manufacturing knowledge can feed into reinvigorating existing buildings and laying over them the things that people expect in the post-COVID world, ideas of natural materials, of spaces that make you feel good, rather than spaces that are crammed full of synthetic materials, that are dark, that are inhumane. And timber can be part of all of those stories. Finally, I am getting to the end, I promise. We've gone at great speed to try and save 10 minutes for questions. But this is just a little example that we're working on in the Netherlands at the moment, which is taking that idea and doing on a slightly smaller scale. This one we're much more hopeful of happening, but it's taking an existing low-level concrete building and reimagining that as new development, but keeping all that carbon in the concrete. So we're really interested in that too. Just because we like wood doesn't mean we want to obliterate concrete buildings. We want to save them. We want to keep the carbon in them for as long as we possibly can. So I'll leave this up on the screen just for a couple of seconds because you might have seen on the way through, there are a few QR codes. Everything that we design, we try to share. We think that's our responsibility. But it's also important that as we go on this journey of building innovative, new, boundary-pushing buildings, that we help other people to do that in a way that is conscientious, that applies the right skills and the right knowledge. So it's really important to us to share this because the last thing the world needs is a failure of one of these buildings. It's really important that we all are super conscientious learning these new technologies, albeit with very old historic materials. So please do, if you've got the chance, whip out your mobile phone. If you want to download any of these documents or learn more about any of the work that we do, it's there on screen. But I think you're probably bored of that page now, so I'll move on. Here's a little bit about who I am. Obrigado. Thank you very much for listening. I hope that was intelligible in my high-speed English accent, but you know, I know this is being recorded, and of course, feel free to reach out on any of the means that are shown here if you'd like to talk to us and understand more about the work that we do.